Welcome everybody. My name is Alexander Hurwicz, and this is the Introduction to Deep Learning. This lecture is number 1 in the course of Deep Learning. Let me present the content of today's lecture. We will start with the story of what Deep Learning is and what it isn't. Next, we will review kinds of Deep Learning. Next, we will talk about typical process of Deep Learning. And then we will talk about key components. We will end up our journey with a story about how artificial neural networks appeared and what was the inspiration for that. So let's talk what deep learning is. We will start from the broader category, and the broader category is artificial intelligence. Artificial intelligence unites a set of various technologies which mimics human behavior. Human behavior means intelligence, skills, understanding of level of language, ability to interpret natural language, hear, talk, and other skills. Machine learning is a subset of artificial intelligence, and its main characteristic is that it is about smart algorithms which can learn from data without being explicitly programmed. It means we don't have to type hard-coded functions, ifs, and other typical traditional algorithms, but rather we define a logic which simulates some kind of intelligence and is capable of learning from data. The deep learning is even smaller than machine learning, while machine learning also includes some statistical approaches like principal component analysis. Deep learning is purely about neural networks. It may solve similar tasks to machine learning, which we will soon see. So let's see what kinds of deep learning problems are there. And we will see that they are pretty similar to machine learning ones. For example, we can see supervised learning, unsupervised learning, and familiar reinforcement learning, but now it is named deep reinforcement learning because at its core, the deep neural network lies. And also we can simulate agent and environment with these deep neural networks, which allows us much more flexible interpretation of those. Also, you will notice online learning, which is meta category, honestly. Typically, when we're talking about machine learning, it is offline learning when the agent does not interact with environment, but in the scope of online learning, this interaction happens, and we have somehow to adapt to it. An example of such algorithm is reinforcement learning, of course, but there are a set of not that smart algorithms, let's say so. Also, you will notice a thing which is called self-supervised, and here we are talking about algorithms which are learning to predict parts of the data using another parts of the data. For example, recently invented transformers are taking a sequence of symbols as input, and part of the sequence is masked. And these algorithms, initial stage is pre-training. They are just trying to predict missing symbols or words. This is called self-supervision. Like the labels and the features are the parts of the same data. Now let's look at the familiar fields, supervised learning and unsupervised learning. You can see supervised learning in a blue rectangle, and we are very familiar with regression and classification tasks. Also, there are modern recommender system, and we know that recommender system selects the best product or item fit for user or customer based on its individual profile, a similarity to other users, or similarity of items. Also, we can see there a sequence learning, and the sequence learning solves the problem when of inconsistent and dissimilar inputs and outputs. We got used to the situation when the size of inputs and outputs are static. If we are working with a tabular data and trained model for 16 features, there always will be 16 features and one target. But what if we are working with video data? And video is just a sequence of images. And in this case, sequence matters. And the same for natural language. Now, let's take a look at unsupervised learning. It is depicted in red. There are such problems as clustering, subspace estimation, generative adversarial networks, and causality learning. Clustering is already well known to us. It is an attempt to separate data based on some hidden structure without knowing the labels. The subspace estimation stands for an attempt to represent some set of data characteristics with a smaller set of characteristics. Generative adversarial networks are trying to generate data which is similar to a given subset. There are generator and discriminator networks. Now let's take a look at a big picture of a typical machine learning and data and deep learning process. So mostly we do the following. First, we collect data, we prepare it, generate features probably, then we separate labels. It's a thing that we are going to predict later. Then we are iteratively selecting and training machine learning algorithms. Here we do hyperparameters tuning, we generate features, we drop features, we learn feature importance and correlations, we change learning rate, and everything which you know probably from the machine learning course. And after that, we're receiving the predictive model. The predictive model now can generalize. It can take in new data and generate desired labels. But the reality is a bit different. After some time, either condition of the model environment will change, will spot some discrepancies of predictions from the desired ones, and gap analysis is a systematization of typical discrepancies and then collecting more data. Having this data, we fine-tune machine learning algorithms, get better predictive models. Now we will go a bit deeper into this process. EDA is when we're trying to understand the data. What is the amount of data? What features do we have there? What features are we going to generate and what features we are going to draw? So a bit separate process is advanced analytics. Advanced analytics often happens as an answer to business questions and then trying to answer with statistical methods, logistic probability, tree feature importance, feature correlations, and other things, or just the best option is to visualize your findings, to present them to your auditory, to yourself, to your customers, to your business owner. Now let's continue with the core process stages. And the core stages include preprocessing, training the algorithm, evaluation of the algorithm, and the prediction, deployment, prediction, and inference. Preprocessing is when you collect raw data and raw labels. You extract scale features to prepare this data to put into the model. The prepared dataset is called dataset, and usually it is split into two or more parts. The simplest setup is depicted here. You just split into 80-20 to training and test. If you have hyperparameters and you want to tune them, you will want to split into training, test, and validation. And if you want to learn the model ability to generalize, you would want to do a cross-validation. So besides splitting the data generating features, sometimes we want to try to reduce a dimension of the data. Each dimensionality reduction has its own measure of importance, and it's not often correlates with your target prediction capabilities. So be careful here. So after the pre-processing is finished, you have your data set and test data set ready to train the algorithm. And now we are moving to the second stage, which is training and learning. Here, first we select the model appropriate for the task. Hyperparameter optimization stands for selection of the best possible learning rate, number of layers in a neural network, number of neurons in the layer. Now imagine the phase 2 is finished and we are moving to evaluation. During evaluation, we measure the metrics which will allow us to understand the algorithm and the solution better and also interpret it for others. For example, for classification algorithms, it is important to measure not only accuracy, but also precision, recall, F1 score, confusion matrix, and AUC metric. They will help you to describe your algorithms and its future behavior. So let's move to stage number 4, and it is inference and prediction. After we trained and evaluated our algorithm, we want to make an inference. Inference is our attempt to understand how it will work on the real data in the real environment. So we are passing the data points the algorithm has never seen before and see its capabilities to generalize in a real environment. Now let's talk about key components. And there are only 4 key components: data, models, loss functions, and optimization algorithms. You can see all of them in this picture. We will start from the training data. The training data is passed to the model using loss function and optimization algorithm, computes the discrepancy of the predicted labels from target labels. Optimization algorithms calculates gradients from these discrepancies, and these gradients later used to update weights of the model, and next step begins. Finally, let's talk about how this science appeared at all. One of the neuroscientists and a computer programmer, a mathematician, were observing biological neurons, tried to build a mathematical model for that, but it was even simpler. They built electrical circuits. There were no computers at that time in the form we have them today. And let's compare these two. To the left, we see a neuron, and 3 major components of a neuron are dendrites, the small heads of a neuron body, and their goal is to accept the signal from other neurons. There are neuron body, and the neuron body makes decisions based on dendrites input, and these decisions are very simple: either to pass the electrical signal through axon or to not pass. The cell of a neuron is connected to another neuron through a synapse. The long tail is connected to the synapse. It is called axon. And now let's take a look to the right. Here is a mathematical model of a biological neuron. To the left, we see blue circles. They are attributes, the parameters we were talking about. The parameters here mimic dendrites of the biological neuron to the left. The neural cell is emulated with this green circle where all inputs from dendrites are summed up and then multiplied by weights. And weights corresponding to the strength of a connection of a dendrites and the neuron core. Then, as I said, the neuron core makes a decision either to pass signal to the neighborhood neuron or not. And this decision is made with the help of the activation function. You see the example of activation function in the orange circle. The step function is there, by the way, and you see its inputs. They are either 1, if the total sum of dendrites inputs multiplied per weights is greater than 0, or 0 if the sum is less than 0. So that's a simple logic of a mathematical neuron, which is very similar to original biologic, to make decisions. Imagine thousands and thousands of millions of that simple perceptrons joined together, where all following perceptrons taking and as inputs signal from thousands of previous perceptrons. And this kind of interaction is repeated thousands and millions of times. So here are takeaways. First, AI algorithms is something that mimics human intelligence and skills. ML algorithms is a subset of AI, and the major characteristic of ML is ability to learn from data without being explicitly programmed. Deep learning is a subset of machine learning. Its major characteristic, neural networks, are extensively utilized there. Deep learning lifecycle is similar to ML lifecycle, except that deep learning doesn't require extensive feature engineering, as the opposite to the machine learning, where we have to extensively preprocess features. To name main components of deep learning are data, models, loss functions, and optimization algorithms. I would like to finish with the fact that the inspiration for creation of a deep learning models was taken from biological neurons by Warren McCulloch and Walter Pitts in 1933. Here is the famous meme. Thank you for attention. Thank you for your time. Please don't hesitate, don't shy to ask questions in the comment section, and see you later.